Hi everyone, this is Mrs. GA. Today we are going to learn how to solve absolute value inequalities. I have a quick warm-up for you guys, so please pause the video and give it a try, and we'll check your answers in just a few seconds. Okay, go ahead and check your answers here. So first, check your graphs. Then here you can see that each one is written as a piecewise function. I want to remind you for the piecewise functions, in terms of including or not including the x value of your vertex, it can be included in either the top or the bottom. It doesn't matter as long as it's not in both. So same thing here. And then you can see for the equations that you can't see what the y-intercept is clearly, you can always use the point slope form, which I did here, to help you make the equations. So you could always use the vertex as a point, and then you know the slope of your lines on the left and right. Okay, so today, remember, we're still working with absolute values, except this time we're working with inequalities. So we're going to learn how to first solve an absolute value inequality graphically. So this is very similar to solving an absolute value equation graphically. We're first going to graph the left and right sides of our inequality separately. And let's graph them pretend like they're just equations when you graph. So I'm going to graph the left side in blue. So there my vertex is -2, 2, and the slope is +1 going to the right. And the slope is -1 on the left. Then I'm going to graph the right side of my equation, which is the constant function y equals 6. So like this. Now, if this were an equation, we would find the points of intersection, and our answer would be the x values of those points. But this is an inequality. So I'm wondering, where is this blue portion of our graph greater than or equal to the red portion of our graph? So essentially, where is the blue above or equal to the red? So you can see that that's happening in two different regions. So it's happening here and here. So those two regions are going to be our answer. So now it's not just a single point or a single value as our answer, it's actually an interval that's our answer. So these are the regions we're going to describe. So let's start with this one. This region is everything from -infinity to this x value, which is -6. So we can say -infinity to -6, including -6 because it's greater than or equal to. And then to describe the second region, we can just put a comma to separate them. It starts here at 2 and it continues to +infinity. And 2 is included, again, because here we have greater than or equal to. So this is our solution. Okay, let's try another one together. If you're following along with my note packet, I've made changes to my note packet, so you may need to update this inequality sign so it says greater than. So same process, I'll graph this portion in blue and this portion in red. So this absolute value portion has a vertex at +1, +3, a slope of -2 on the right, and a slope of +2 on the left. And then my other function is a constant function at y equals 1. So here, again, we're wondering, where is the blue greater than the red? So here you can see that it's actually a confined interval, so it's from here to here, and it is just greater than, not greater than or equal to, so we will not include those values as part of our answer. So it would look like this. So how do we write that in interval notation? The lower boundary is 0, the upper boundary is 2, and neither are included. So here we just have a single interval that would be our answer rather than two different intervals. So now we're going to talk about how to solve an absolute value inequality algebraically. So we're always going to start by isolating our absolute value term, and then we're going to create two separate inequalities, just like when we're solving an equation, one for the positive case, one for the negative case. But here, we need to be careful when we do that, because for these, you're either going to have what's called an or answer or an and answer. So you're going to either have two separate intervals or one single interval, and that's going to depend on the direction of your inequality symbol. So after you've isolated your absolute value term, if you see that your absolute value term is greater than, I say greater becomes or. And if you see that your absolute value symbol is less than, I say less than and, it becomes an and answer. So again, anytime you have your absolute value greater than, it's an or answer. Anytime it's less than, it's an and answer. And we'll talk about what that looks like in the next example. Okay, so let's try solving this algebraically. So again, let's start by isolating our absolute value symbol. So we can start by subtracting 1 from each side, and then we can divide each side by 2. Okay, so here we are going to create two separate inequalities, but remember, we have to either decide if it's an and or an or problem. So here it's our absolute value is greater than, so it's great or, so we use or. So before I do anything else, I'm going to write or so we remember. Now here we're going to create the two separate cases. So imagine that whatever was inside our absolute value sign, which in this case is 3 minus x, imagine that 3 minus x ends up being a positive value. That means that essentially the absolute value signs aren't doing anything, and it really wouldn't change our inequality at all. So it would just stay the same, like this. Now imagine a world where 3 minus x gives you a negative value. Of course, the absolute value signs would turn it to positive, but imagine that it were negative, this value were negative. Let's consider that case. So if this were negative, and imagine we divided the negative to the other side, when we divide by the negative, we have to flip our inequality sign, and then the value becomes negative. So again, this is the case where 3 minus x was positive. This is the case where 3 minus x gave us a negative value, and we're dividing it to the other side, which flips our absolute value sign. Now we can finish solving these separately. So here we can subtract 3 from each side, and then we can divide both sides by -1, which will, again, flip our absolute value sign anytime we multiply or divide by a negative. I'm going to write or with every step so we don't forget. And then let's finish solving same way on the right. And then when we divide by -1, don't forget to flip your inequality sign again. So our answer here is x is less than -4 or x is greater than 10. So that is our answer. And the reason why it's an or, if you sketch this out on a number line to see what's happening, it's actually two completely different intervals. So say here's -4 and here's 10. It's everything to the left of -4 and everything greater than 10. So there's no possible way for it to be this and this. It is important that we know this is this interval or this interval because there's no overlapping. And also notice I did open symbols here because the values are not included. Okay, let's try another one together. So here our absolute value expression is already isolated, so I'm ready to set up the two separate inequalities. Here our absolute value is less than, so remember less than are ands. So we have something and something. So again, imagine 2x plus 8 was positive. That would not change anything about our inequality. Now imagine the scenario where 2x plus 8 gave us a negative value, and then imagine we divided that negative to the other side. That would flip our inequality symbol and make the 6 negative. So we're going to finish solving here. So 2x is less than or equal to negative 2. X is less than or equal to negative 1. And then finish solving here. So 2x is greater than or equal to negative 14. X is greater than or equal to negative 7. So our answer should be everything less than or equal to negative 1 and everything greater than or equal to negative 7. So this we can actually write as a single inequality. So it's everything greater than or equal to negative 7, but less than or equal to negative 1. So we can write any and answer as a single inequality. And this is what your final answer should look like. If it helps, you can kind of sketch out what's happening here. So here's negative 7, here's negative 1. So our solution says it's everything less than or equal to negative 1, which would be like this, and everything greater than or equal to 7, which would be like this. Now, since it's this and this, it has to work for both inequalities, which means it's going to, your answer, your final answer is going to be where your lines essentially overlap. So our final answer would be this region, again, the region that works for both inequalities, which is why we're going to write it as a single inequality. All right, so at this time I'm going to ask you to pause the video and give these two a try, and we'll check your answers in just a few seconds. All right, so go ahead and check here. So by the time you've isolated your absolute value for part A, notice that when you do this step, when you're dividing both sides by negative 1, it flips your inequality sign. So since your inequality is less than, this is an and problem. So you get x is less than 5 and x is greater than 1, which would be everything between negative 1 and 5, not including either. And then for part B, by the time you isolate, your sign again has flipped. So this is a great or than, so it's an or problem. So here's your two scenarios, and your answer should have or. So it's two separate inequalities as your answer. Okay, the last thing we're going to talk about today is how to model a real-life scenario with an absolute value inequality. So let's take the case where a box of cereal is supposed to weigh 13 ounces. Like the manufacturer produces it and it's supposed to weigh 13 ounces, but it's acceptable for the box, the weight of the box to vary by as much as 0.2 ounces. So when it says vary by as much as, it means it could be 0.2 above or 0.2 below, meaning either way is fine. Model the following scenario with an absolute value inequality where W represents the weight of the box. So just to kind of visualize the kind of interval that would work, so the upper end of what's acceptable would be 13.2 ounces. The lower end of what's acceptable would be 12.8 ounces. And again, 13 is kind of like that ideal point, but again, it can vary by this much. So how do you represent that with W, where W is the weight of the box? Well, the difference between the weight, so the actual weight, and 13 ounces should be no more than 0.2. So again, that's the difference between the weight and 13 should be no more than 0.2. Now, since it's 0.2 above or below, we can actually do absolute value. So again, if it's below, so it's less than, it will take that 0.2 and it will make it positive. It's above, we'll take that 0.2 and it'll make it positive. Well, it's already positive. But again, anytime you're working with a difference and it should be the same above or below, that absolute value sign kind of fixes that scenario. And again, this difference between the actual weight and 13 should be less than or equal to 0.2. Okay, so that's how we can model this scenario with an absolute value inequality. Okay, that is all for today's lesson. Thank you guys for watching.